Hello everybody and welcome to the third episode of our series entitled Bayesian Inference, and in today's video I will discuss with you how we do linear regression with usage of maximum likelihood estimation. As we may know that the linear regression is a very common problem in machine learning. It may be the first lesson everyone would learn when he learns statistics or machine learning. The idea is very straightforward. Suppose we have two variables like the height and weight of a group of people, and we believe that these two variables are linearly correlated to some extent, and therefore we want to obtain a linear function or a linear regression function such that we can use this function to predict one variable given the other variable. So for instance, if we consider the height is the regressor or the predictor variable and the weight is the target variable, we can have a line like that defined by m times height plus b, where the m is the slope of the line and b is the base or the intercept of this line, such that we can predict the value of a person height given his or her weight. So this is simply the idea of linear regression. Usually the easiest way to obtain the linear coefficients of this linear regression problem b and m is a technique called ordinary least squares approach, where we optimize this function using a function called the sum of squared errors. The sum of squared errors is a function of parameter w, which is the vector of coefficients of linear coefficients in our problem, and this minimum squares error function is nothing but the differences between the true values and the expected values of the target variable y. So we sum up the differences and raise each difference to the square, because it can be either positive or negative difference between the true value and the regression line, and we sum up all of these differences, which is also called sometimes residuals, and we divide the summation by n, where n is the number of observations in our problem. So this is the easiest way to find the regression line, and I have already two videos about this technique where I explain in depth how it works and how we can find or estimate the values of the vector w. Here w is the vector of both base and slope of the regression line, and f of x and w is our linear regression function, which is b plus m times height in our example here. So we are okay with this ordinary least squares function, but we need to upgrade to another probabilistic approach, which is called the maximum likelihood approach. So when we move from one approach to another approach to solve the same problem, we usually expect some advantage of using the new approach. And in maximum likelihood, we already have a very nice advantage of employing such probabilistic approach over the OLS approach with the problem of linear regression. So first of all, we have to say that the maximum likelihood regression is identical to the OLS regression approach, which means that the regression line we obtain by using the maximum likelihood approach is identical to the regression line we obtained when we employ OLS technique. simply because maximizing the likelihood function of our data is equivalent to minimizing the ordinary least squares error function. So we obtain the same regression line in both approaches. The advantage of using ML approach is, however, we obtain an extra statistic about our regression analysis, which is the noise level or the uncertainty level that comes with our predicted values. So we obtain a regression line plus the level of uncertainty or the level of noise that's surrounding our predictions when we are employing the maximum likelihood estimation. So we model our data by using the same regression function we use in the OLS technique. We say that the target variable y is equal to a function of both predictor variable x and list of coefficients w, and we add an extra noise parameter epsilon. This extra parameter epsilon we assume, or we suggest for simplicity, that this noise variable is normally distributed, so it is a normal distribution of values with zero mean and constant variance sigma square, which means that the maximum likelihood approach will return a constant noise value or a constant variance value over all our predictions. Therefore, we define our probability function as a normal distribution again. So we believe that the regressor or the predictor variable x is normally distributed with an average of the function of x and w, so the regression line, and the variance is the constant variance regarding the noise that come with our specification. So the idea here is that we consider the output, or we consider that the prediction value is defined by two values, or is defined by a normal distribution that comes with two moments or two instances. The first instance is the predicted value itself, which is nothing but the regression line or the regression function we employ, and the noise level or the uncertainty level is nothing but the constant variance that we define in our noise parameter that we have already added to our data, or we have already assumed to be existed in our regression function or in our data. So if we have already a data set of observations, the likelihood would be the product of all the probabilities of this function. So we move over all observations and we multiply the generated probabilities of this normal distributions over all observations between the true values and the expected values. And this is the definition of our likelihood function that expresses our predictions. In order to obtain feasible results, we need to convert the product into a summation process, such that we add up the probabilities instead of multiplying them, because as we have already mentioned before in our previous videos, that multiplying multiple probabilities between 0 and 1 shall converge the end result to 0, and this is something that we don't want. So we take the logarithm of the likelihood such that we sum up these probabilities instead of multiplying them. So we convert the product into a summation, and we take the logarithm of this normal distribution. The logarithm of this normal distribution is expressed as minus n by 2 times log 2 pi minus n log sigma minus 1 by 2 sigma square times the summation or times the error function that we have already defined in the OLS technique, the sum of residuals or the differences between true and predicted values of our model. So this is the definition of our likelihood function when we take the logarithm of it. And now the goal is to find the missing parameters W, the list of linear coefficients, and sigma square, which reflects the level of uncertainty or the noise level that comes with our predictions. In order to find these two parameters, we differentiate the logarithm, the logarithm likelihood function with respect to W and sigma square in turn. So we begin by differentiating the log likelihood function with respect to W and set the first derivative to 0. And by solving this equation, we find that the W of the best fitted line is defined by the multiplication of T transpose times X all to the power of -1 times X transpose times Y. And if you reviewed my videos about the OLS linear regression, you will find that this estimation of the coefficients vector W is equivalent to the estimation of W we have already obtained using the by minimizing the error function in the ordinary least squares approach. So this is why we say we have said that both approaches, both OLS and ML approach, generates exactly the same regression line with the same level of precision without any differences. Next, we differentiate the logarithm likelihood function with respect to sigma square in order to obtain the constant variance of the noise variable of our regression function. And we set the first derivative to 0. By solving this differential equation, we find that the variance estimation is nothing but the summation of residuals between true and expected values. So when we solve this differential equation, we find that the sigma square is the summation of differences between true and predicted values, all to the power of 2, and we divide the result by the number of observations, which reflects that the level of variance here, or the level of noise that surrounds our regression line, is nothing but the residuals, the summation of residuals that came with the regression line, and we normalize it by dividing it by the number of observations. Now we will have a look at how we can evaluate this technique and which results we could obtain about it. So I have generated this synthetic data set with two variables, X as the regressor or the predictor variable and Y as the target variable, and this data set is defined by minus 0.3 as the bias, plus 0.5 as the intercept, as the slope of the relationship, of the linear relationship, times X, plus a noise parameter which is normally distributed around 0 mean and 0.04 variance. By applying our maximum likelihood approach, we obtain this regression line, and again this is identical to the regression line generated by the OLS technique. However, we have surrounding uncertainty level and a noise level that comes as a bonus of using or of employing the maximum likelihood approach to our problem. And this level is nothing but the normalized summation of residuals between true and predicted values, and this is how we can visualize the level of noise or the level of uncertainty of our prediction model, such that when we say that employing the generated linear regression, we have already or we can estimate the value of y given a new value of x. But we learn that this value of y comes with a certain level of uncertainty or certain error level that can be either more or less the expected value. I've also tried to employ the same linear regression technique with a more complicated function or a highly polynomial function. I have defined this function as y equals 0.5 plus x squared. So it is not 100% linear, but it has almost a single trend. So x is either constant or increasing I'm sorry, y is either constant or increasing with the increasing of x variable. And the technique managed to find the correct regression line. Also, it is not 100%, but it has almost one trend, so we don't have a lot of ups and downs with of variable y when we move when x grows. Y is either constant or growing with x. So the linear regression technique here managed to find an acceptable regression line to some extent. If we move, however, to more sophisticated definition of y, so here we employ the sine function to the regressor x, such that we obtain this highly polynomial function or highly non-linear function with a lot of trends of y with the growth of x. So y value is just moves ups and downs with the growth of x. And when applying the above technique, we find that the maximum likelihood for linear regression failed to find the proper curve that can follow the change of variable y with the growth of variable x. This is simply because, as we have learned before, the non-linear regression approach needs to add an extra parameter called a regularization parameter or a penalty parameter to the error function or to the likelihood function in order to follow the different trends or the level of polynomial function that defines the variable y in terms of variable x. And this is something that we didn't add to our maximum likelihood approach, and this is why the above model failed to follow the exact definition of y. In the upcoming videos, we will see that when we employ an empirical definition of Bayesian approach, which means that when we add a prior distribution to the likelihood distribution, we will see that we can obtain the regularization parameter values automatically when employing this empirical Bayesian approach. And this is something also some advantage of using the Bayesian inference in the problem of nonlinear regression, such that we do not need to tune this regularization parameter such that the resulted curve is either is neither underfitting or nor overfitting the result or the obtained result. We obtain some very well-shaped curve, some very well-defined curve in terms of nonlinearity. And this is something that we will learn in the upcoming videos. So this was everything about linear regression with maximum likelihood estimation. Thank you so much for your time. If you have any questions, make sure to leave it in the comments, and I will do my best to answer it. I will also leave in the comments below the implementation in Python of this technique. So if you want to try it out yourself, you can find it on my GitHub account. And this was everything about this topic, and thank you so much.